In 1922, an American physicist named Arthur Compton, as shown here, noticed that when X-rays were incident upon matter, some radiation was scattered in different directions. And it was this experiment that could not be explained by classical wave theory. Why? Well, it turns out that the scattered radiation didn't have the same wavelength as the incident radiation coming in. Classically, it was expected that the scattered radiation would have the same frequency and wavelength. So this experiment is further evidence of the particle nature of light waves. Okay, let's now explain it using particle theory. In this experiment, the incident radiation is really an incident photon. This photon here collides with a stationary electron, which is at rest and is basically matter. The electron recoils off. It gets scattered, picking up some momentum and energy. The scattered radiation, or should I say scattered photon, basically moves off in this direction with a different wavelength than the incident photon that came in. So the incident wavelength lambda 0 here and the scattered photon wavelength here is different. It shifts. The wavelength of the scattered photon turns out to be greater than the wavelength of the incident photon. And remember, classically, we expected that the two wavelengths and frequencies would be the same for the incident and scattered photon. Well, why is this wavelength different? Well, the reason is that some of the energy of this incident photon is lost and transferred to the scattered electron, picking up kinetic energy. So therefore, the scattered photon has less energy than the incident photon. And remember that E equals hc over lambda for a photon. And because the scattered photon has less energy than the initial photon, then it'll have a longer wavelength. So then the question is, how does this wavelength here, the scattered photon, compare to the incident photon's wavelength? And there are two key principles that we need to use to kind of find that shift in that photon wavelength. We need to use conservation of momentum and also conservation of energy. Okay, let's start off with the momentum picture, which is shown down here that we're going to get to. First of all, recall that a photon has momentum. The momentum of a photon is really the photon energy divided by the speed of light, which is represented with a c. So maybe I'll just write this as a formula. It's really E over c. And the energy of a photon is hf over c, or often you could rewrite this as simply h over lambda, which is shown over here. So the momentum of the incident photon, which is completely along the x-axis, is h over lambda sub 0. The momentum initially in the y direction is 0 because both of these are set to go along the x-axis. And also recall that the momentum of an electron, which has mass, is simply just mass times velocity. So the momentum of the electron is the mass of the electron times the velocity. But you'll see that this electron is moving at an angle, so we'll be using the x and y components. So looking down below, you can see that what we have here is a conservation momentum along the x-axis. There's the incident of momentum of this photon completely along the x-axis. There's no momentum of the electron initially because it's at rest. And then these are the two components of the scattered photon and the scattered electron, their momenta along the x-axis. And then here we have a sine now angles in here because we're looking along the y-axis. No momentum initially in the y direction, but the momentum of the y-axis of the photon here is balanced out by the momentum of the y-axis for the electron. Okay, the next part of this picture is conservation of energy. The energy of the incident photon, so I guess we could write that as E, is equal to the energy of the scattered photon, which is E, say, primed, and then the plus the kinetic energy of the electron. So this energy is now equal to, essentially, the energy of the scattered photon plus the kinetic energy that is gained by the electron. So if you look down below, we have this statement. You have to remember that the energy of a photon is given by this equation, hc over lambda. And remember that the kinetic energy formula for an electron is 1/2 mv squared. So we have the energy of the photon initially, and then we have the photon energy of the scattered photon here, and then the kinetic energy. So you have three equations, 1, 2, 3, and through a number of manipulations, Compton derived, and I'm just going to jump down to here, this equation. Now, this equation is not listed. This is the Compton Shift equation, essentially. This equation is not listed on the AP formula sheet, so my guess is you're not responsible to know how to use this equation necessarily, because they don't really give it to you on the equation sheet. And I don't think you would actually have to derive it. I think it's quite complex to derive in a short time period. So I think what's most important, what you should know of the Compton scattering, is really you should be able to describe the experiment, state the results, such as the Compton wavelength increases. If you look back to here, we said that this scattered photon has a longer wavelength than the initial wavelength. And why is that so? Well, that's because some of this incident energy that comes in is transferred to kinetic energy, so the energy of the scatter photon is less, and because it's less energy, it's going to have a longer wavelength. Things like that you should know. There have been some past FRQs that have kind of used these principles, but they're relatively straightforward to solve, so they're nothing too complex. All right, that's all I want to say about the Compton effect.